Um, yeah, so today, I think in the last lecture, what we covered was Einstein's coefficients. We covered that when when we start the derivation for light atom interaction, uh, we start with the formalism that the electric field, if we are doing semi-classical analysis, by semi-classical, I mean we are treating the atom as a quantum system, and we are treating the light as a classical system. So light is basically an electromagnetic wave, and atom acts as a two-level system, which acts as the dipole. So it's basically a system where we are studying changing electric uh, field's impact on the dipole, and then the dipole radiates, and then we are analyzing now if the radiation is quantized. I mean, I guess that's the next step, but we are right now analyzing if the atom is just a two-level system, then what are the different scenarios that we can uh, analyze in this problem statement. So there are two different scenarios that we talked about last time. One of which is if the radiation is broadband. So if the incident laser that we have incident on the atom, if that is broadband, what that means is if that has a lot of frequencies in it, then we will get uh, a different spectrum. Like depending on like the reaction of the atom will be different if the frequency that is incident is broadband compared to if the frequency that is incident is monochromatic, which is like a very narrow range of frequencies that you have incident on that. So you can incident like I said in the experiment as well, you can incident the broadband laser. And in the experiment, you can also incident like a narrow, very narrow laser, which is monochromatic laser. So last time we talked about Einstein's coefficients, which basically tells you that in the two-level system, there are only three processes that can happen. One is the atom's entire population, which is basically the electron is starting in the ground state, which is the zeroth state, and it's exciting to the first excited state because of the laser that we are incidenting. So there are only three processes that can happen in the two-level system that is interacting with light. Either the entire population gets transferred to the first excited state. Uh, so there are two processes which are one is stimulated process and another is spontaneous process. So spontaneous process is the one which we are not carrying out, which is happening by itself, which is a natural process. So spontaneous emission happens by itself, but it happens because of the interaction with vacuum. So if the system is excited, then the excitation gets de-excited. So basically, the electron gets down from the first level to the ground state again. That happens by itself. If that happens by itself, we say it's a decay process, or in other words, we say it's a spontaneous emission process. If we did anyone join? Okay, yeah, sorry about that. So the process of coming from the excited state to the ground state happens only um, can happen spontaneous way, but the other process cannot happen by spontaneous. So there is no spontaneous absorption, of course, but there is a spontaneous emission. And if you are stimulating the system, if you are incidenting a laser, then stimulated processes can go both ways. So there can be a stimulated absorption or there can be a stimulated emission. And with each three processes, we have associated a coefficient. So A is a coefficient which is associated with A21 to be precise, is a coefficient which is associated with spontaneous emission. B21 is the coefficient that is associated with stimulated emission, and B12 is the coefficient that is associated with stimulated absorption. So if these three processes are what we need to consider whenever we are considering the excitations that are possible, excitations and the excitations that are possible in our system, which is a two-level system, then we get Einstein coefficient. And Einstein coefficients basically give us the relationship between these coefficients, how they are related. And it also makes a simple assumption that the total population in the levels have to be conserved. If we just take these two simple things into account and then we derive everything from the Planck's distribution, then we get the relations between these Einstein's coefficients, and those prove useful whenever we are trying to guess what are the properties of our atom. So each atom is different. So when we are considering the atom as a two-level system, if we are considering very different atoms like lithium or cesium or many different atoms that we do research in actual like real world, then in that case, what we do is we take the atom as a two-level system, but then what changes is the coefficients. So these three coefficients change for each atom, and then these three coefficients are using which we say that these are now the properties of our atom. Because then the spontaneous emission coefficient will change, and there will be different decay channels in different atoms, because then in real atoms we don't even deal with two-level system, we deal with multi-levels. And then there is a formalism that you can use, that you need to do summation over all the different levels, but that is easily extendable. If you understand the two-level system formalism, then that you can extend this formalism to multi-levels, and it's not very difficult if you have a background of Clebsch-Gordon coefficients, which I think you will study a lot maybe in atomic physics, like in the fourth semester. But Clebsch-Gordon coefficient in simple language basically gives you the probability of going from a specific level to a specific level. Because if there are multi levels, if there are many possible levels to which the electron can go in the excited state, then given that it has a lot of options, there are certain probabilities with which it can go to each different level. So, and that those probabilities are governed by the Clebsch-Gordon coefficients. And the Clebsch-Gordon coefficients actually are determined according to the stability of that level. So, if the level is more stable, then the Clebsch-Gordon coefficients will be high. And basically, what that does is there is this transition, a transition to that level which is more stable is more probable. So anyway, so that's what we studied last time, like Einstein's coefficients. That formalism is mainly for the broadband source. So if we have a laser which is huge, which has huge width in frequency, so it has frequencies from all over the place, then the interaction of atom with a broadband source is mainly studied in terms of Clebsch-Gordon coefficients. But today we will learn about the other scenario, which is the interaction of monochromatic light with the atom. So chrome, chroma actually means color, and monochromatic basically means of single color. What that means in scientific language is basically you are talking about a light which is of single frequency or single wavelength. So, but then if you can't have a laser light, or if you can't have any source of light which is of a single frequency, because when we talked about the real life light sources, they always have a width. Um, Either that width can be very small or that width can be bigger, but it definitely has a width. So it cannot give you, any light source cannot give you basically a single frequency. It will give you a range of frequencies. So F or omega plus or minus d omega. So d omega is the frequency range that I'm talking about. So even if you have a very narrow source, it has a finite d omega. So we generally won't have any source in real world which gives you uh, a source that you can incident on an atom that has no width at all. So that is of specific frequency. So you'll always get a width, but if the width is narrow, then you can consider that source to be close to monochromatic. So that's what we will consider today. That if we have such a laser, if we have such a monochromatic light source, if we incident that on atoms, then what will happen? So let's continue that. So in that context, if we again see whatever we derived last time, so these are the equations actually we talked about last time a lot. So these are the coupled differential equations that you get when you solve for the dipole matrix element, like we did last time. And if you remember our notations, then the capital omega was Rabi frequency, small omega was the laser frequency. So the frequency of light that we are incidenting with, and omega naught is the resonant frequency. So what do you mean by resonant frequency? It is the difference, or it is the required frequency difference between the levels to go from one level to another level. So omega naught is the resonant frequency. So that is a property of an atom. Omega is the incident frequency of the laser. So that is the property of a laser. And then capital omega is the Rabi frequency, which gives you basically the coupling between the first excited state and the ground state. Um, and that coupling basically gives you the coupling strength. What that means is omega characterizes, so capital omega characterizes the light atom interaction, how strongly the light couples the two levels of the system. That's what we characterize by capital omega. So small omega gives you the laser's properties, and omega naught, small omega naught gives you the properties of an atom. So that's why these are the three things. And C1 and C2 are the coefficients for the first level and the second level. So this is what we talked about last time. Last time, what we derived was for weak excitation. So if you, what do I mean by weak excitation? So when I'm saying weak and strong with respect to a laser, I'm talking about the intensity of the laser because the laser's frequency is constant, and we are not right now talking about the phase of the laser. So only part that we are changing is the intensity of the laser. And intensity is kind of something that you can say in terms of omega square. So whenever consider that whenever I'm talking about the intensity of the laser, I'm talking about the omega square, which is like Rabi frequency square. So because Rabi frequency square is kind of in the same, you can imagine Rabi frequency square to be very similar to intensity because then I can maybe tell you the motivation for that later, but understand that whenever I'm talking about weak and strong, I'm talking about higher Rabi frequency or lower Rabi frequency. And Rabi frequency basically gives you how strong is the coupling between the two levels of our system. And that coupling is there because of the laser. So if you remember the formula for omega, then um, this is just a quick recap that omega was actually the matrix dipole moment with h bar coefficient. So this gives you, so D is the dipole moment and E is the electric field. E is the electric field that is because of the laser, and D is the dipole moment because of the atom. That's why this omega gives you the coupling strength. So these are the equations that we are considering even the last time. So what we will change here now is now omega is significantly higher. So omega is strong, capital omega is strong. So that's why basically we are dealing with higher Rabi frequency. So now, when we will consider these equations, if you substitute cos omega t as exponentials, e to the power I omega t plus e to the power minus I omega t, if you do this substitution and if you do rotating wave approximation, that is also simple. Last time we talked about this, that rotating wave approximation basically means that you are very close to resonance. And if you are very close to resonance, then the right hand side of this equation, omega minus omega naught, becomes very close to zero. And then this becomes very close to 2 omega naught. So that's why the left hand side becomes much larger and you can ignore the omega minus omega naught terms. Um, Actually, why you won't ignore those is because those are in the exponentials. And then whenever you're considering a high frequency term, that means that omega is high. And at the start, we have talked about omega being always the angular frequency. So if omega is the angular frequency, then those are the very fast rotating components. So then you can ignore their rotation. That's why actually there is a formalism that tells you that even those are slightly not non-physical terms. That's why we will ignore those and we will keep one of these. That's why we only keep omega minus omega naught. So we go from this to this by just these two steps, by substituting cos omega t and by doing rotating wave approximation, which is basically you're ignoring the fast rotating terms in your Hamiltonian. So if you do that, then you get these equations. And then if you solve these equations, which is basically your what you're doing is you're differentiating the second equation with time, then you will get double derivative on the left hand side. And then basically after after substituting the first equation, you will get everything in terms of just C2 and everything in terms of just C1 if you do it the other way. So you have basically decoupled the equations that were coupled in the first place. And if you decouple, then you can find out the coefficients C1 and C2. And since you are interested in the coefficient C2, because that's the excited state coefficient, then you will get an expression. So this is the differential equation that you get. These are all simple steps, I think, and if you do it by yourself, you can just quickly do it. That's why I didn't derive it here. I just took notes from the foot book. So this is these all these expressions are from the foot book itself. So if you take this expression, because I mean the reason why I'm not interested in algebra a lot is because something that we can take away from this is after all these steps are done, once we reach the final equation, there is a lot of physics that we can understand from that equation. So that's why I wanted to emphasize more on that physics rather than doing algebra with you, because these steps are pretty simple and you can go through them by yourself. So you get this differential equation for the second coefficient, for the coefficient of the second level. And then if you start from the ground state, so at the start, if you have a two-level system and all the population is in the ground state, and then you have excited from using the laser of specific frequency, then what you will do is drive oscillations between the system, and then the coefficients will be time dependent because the population will get excited to the excited state, and then it will come down. So the population then becomes time dependent, and then the time dependence is what we can get out from the solution of this differential equation, because we have been deriving everything in terms of taking derivatives in terms of with respect to time. That's why what we get as the solution of this differential equation is this expression, which if you see that C2 coefficient is time dependent, and if you take square of that, you will get everything in terms of omega, capital omega, and the frequency difference, which is omega minus omega naught. So this gives you the difference between laser's frequency that we are incidenting and the resonant frequency of our system. So if we are on resonance, if we are at resonance, then that means omega is equal to omega naught. So since we have this expression now, where W is one quantity that they have defined in terms of Rabi frequency. So in terms of Rabi frequency and in terms of how much away you are from resonance. So you will always notice in atomic physics systems that capital omega, which is the Rabi frequency, and delta, or it is also used as a capital delta. In some books they refer to it as capital delta. So either small delta or capital delta, the notations change according to the reference book that you use. So these are the two quantities that are very useful even theoretically and experimentally, because capital omega gives you the coupling strength between the interaction strength basically between the light and the atom that you are using. So omega, yeah, this defines the light atom interaction, and this defines whether you are on resonance or not. So delta gives you whether you're on resonant or off resonant with respect to the frequency that you're incidenting, and capital omega gives you the light atom interaction strength. So these are the two quantities actually using which we want to discuss everything that in the rest of the lecture. So these are very important even experimentally, because the physics that governs and the equations that comes out of these equations is very different if you are considering on resonant interaction versus off resonant interaction. And also it is very different when you're considering the interaction strength is if it is pretty low or if it is pretty high, then very different kind of physics happens in atomic world. So if we now take a graph of this expression that we have got, then after simplification, because we are at resonance, we will substitute omega equal to omega naught here, and then that becomes basically omega is same as W is same as capital omega, and then the expression simplifies as sine square omega t by 2. So basically what this is the uh, sine square x function, and that if we plot that function, so if we exactly plot this, so on this axis we have a phase, and on y-axis we have the probability. So y-axis gives you the probability of being in the excited state, So if the probability of being in the excited state is 1, then all the population is in the excited state basically. And if the probability of being in the excited state is 0, then all the population is in the ground state. So that's why it goes from 0 to 1. And then on x-axis, what you get is time, but they have converted it to phase. So they are considering from 0 to 4 pi. So actually, yeah, this is time, but they have plotted, I think, in terms of omega t, so which is a phase. So now what you consider is if, so now let me tell you the full story that if you incident a laser which is monochromatic on an atom which is a two-level system, then if you're doing it on resonance, so then if the frequency that is incident matches with the frequency that is of the resonance of the system, that is basically the resonant frequency between the two levels. So if I want to draw you a diagram, then let me just quickly draw you a diagram so that it's easier for you to imagine this. So basically, because this is the full picture now, if you have two levels and they are separated by omega naught, and then you are incidenting a laser on it, which is of frequency omega, specific frequency omega, then so on resonance, omega equal to omega naught, and with a specific interaction strength, which is the Rabi frequency, uh, which is given as this expression, then the physics that you get is basically the populations oscillate between the two levels. So if you start with your electron being here, after a while the electron will go here. If you have multiple systems like this, then you're talking in terms of populations. So then there is a probability that the electron, if the electron starts in the ground state, there is a probability after a certain amount of time that the electron will be in the excited state. And then it will go up, it will come down, it will go up, it will come down. So then this will continue. These oscillations from the ground state to the excited state and back, these will continue if you have your exposure of the laser on the atom continuously. So these oscillations between the two states is what we call as Rabi oscillations. And the concept of Rabi oscillations is very important in the two-level systems because there are different two-level systems that are that you can consider. Spin half is also another two-level system, like a spin half particle, because the spin half particle has two quantum levels because of the spin operator. So it has plus half and minus half. So it can take two values. That's why it has two levels. So it can oscillate between plus half and minus half if you excite that system. Those are called Rabi oscillations in that system. In our system, because our two-level system is atomic system, um, where we are considering the electron going from the ground state to the excited state and coming back. Then these are the Rabi oscillations in atomic physics. So Rabi oscillations basically give you the oscillations between the two levels of your system excited because of the laser that you're incident. So you can see the behavior here because it's a sine square x function. You can see the maximum is at pi. So what will happen if you keep omega t as pi? Actually, this should be omega t. So if you consider that if you do, if you take, yeah, if you take omega t as 0, then at the start, like at time t equal to 0, at the start you will be at the ground state. So you'll start at the ground state. And then after a time interval, if your omega t becomes equal to pi, then all the population goes to the excited state. So basically at this point here in the graph, so you started with this point in the graph. And then after a while, after the phase pi, what you'll get is all the population from the ground state is excited to the excited state. Then it will come back. So this is basically, this happens because of the this happens because of the stimulated absorption. And then after a while, if you continue imparting your laser on the atom, then From the first excited state, it will come down and it will reach again the ground state. And these oscillations going up and coming down, these will continue. And then what you'll get basically is in the time picture, you'll get this graph. So now it depends whether your population will be completely in the excited state or not, whether you're on resonance or not. So this capital delta here, this being zero basically means that omega is equal to omega naught. So you're on resonance. So how much away you're from resonance? So basically, if you incident any frequency laser on an atom, and if you are considering a specific transition, that transition is a specific frequency omega naught. If your laser frequency matches with omega naught, then the complete population from the ground state will get excited to the excited state. If your laser's frequency is not the same as omega naught, then the entire population will not get transferred, and then it will actually depend on um, how much population you are exciting. So if you don't want to excite the entire population from the ground state to the excited state, then don't be at resonance. Be away from the resonance. Then you can decide how much population you want to take it to the excited state and how much population you want to come back. So this basically gives you a tool now, right? To manipulate the atomic system and to transfer populations from the ground state to the excited state. And how much population you want to transfer, that also you can decide. So this basically gives you a nice tool to manipulate the atomic system. And like we talked about in the earlier lectures as well, that the lasers concept basically is also the first step in the lasers concept is also population inversion. So whenever you want to invert the system, what do you mean by inverting the system? You mean that all the ground state population going to the excited state, and that you can do now. You can understand that now in terms of on resonant interaction. So that's why I'm talking a lot about on resonance versus off resonance, because off resonance, if your laser frequency is not same as the applied frequency, then you won't be able to transfer the entire population. And you also kind of so now intuition wise, if you have an atom in your lab, if like we deal with atoms in the lab all the time in Purdue. So if we have an atom and then if we incident a laser on it, depending on whether the laser is on resonant or off resonant, we will have very different interaction. Where we will have very different excitation. So there are different cases that you can consider when you're considering the interaction, but remember that on resonance, you will always get Rabi oscillation. So, and in the atomic systems, you'll always get Rabi oscillations, and those are kind of the signatures of your system. So, your system will be characterized by what is the Rabi frequency period of your system, what is the amplitude to which you can go, and what is the decay rate and everything. So, that's why whenever you have a system which is like an atom, you can, and for a specific light laser, then you can characterize your setup basically in terms of these parameters and this process as well, which is called as Rabi oscillation. So Rabi oscillations basically is a process in which your atomic population or your electron basically goes from the ground state to excited state and comes back and keeps oscillating. And those oscillations are periodic, and those are called as Rabi oscillations. And the term Rabi comes from Rabi frequency, which we have talked about earlier, which signifies the interaction between the light and the atom. So the different cases that we can see in Rabi oscillations is if so there are three quantities here that we are always talking about, right? Omega, capital omega is the Rabi frequency. So if capital omega is large, then there is a large coupling strength. So that's why that can happen because of two reasons. Either you have a strong laser or you have a strong dipole. Because the D dot E term, one of those has to be strong. In only in that case, your capital omega becomes large. So that's why if you're talking about Rabi frequencies, you can talk about two regimes where the Rabi frequency is low either or your Rabi frequency is high. In frequencies, in a different frequency, you can always talk about another two regimes, which is on resonance and off resonance. So again, on resonance means that your atomic resonance is exactly same as your applied frequency. And if your atomic resonance is not the same as applied frequency, that means you have a detuning in the system. Detuning basically means that omega minus omega naught is not zero. The difference in the frequency is called as the detuning of the laser. And if your laser is then detuned, then this detuning, represented by capital delta here, that physics that you will get will be very different compared to on resonance. That's why whenever you're talking about this interaction of light and atom, you need to be very specific about which regime you're talking about. So either you can be on resonance, either you can be off resonance. You can have a low coupling strength, you can have a higher coupling strength. Another regime that we talked about was either you can have monochromatic laser that is incident on the laser, or you can have a broadband laser that can be incident on the atom. So basically, the width of the frequencies that are you're incidenting, that can be large either, or that can be small, and that changes the physics that you will see in the experiment. Okay, there is a question: are the Rabi oscillations sustained only because the system is still exposed to laser, or there is any possibility for damping? Yeah, exactly. So I'm coming to that only. So this is the excitation that we are doing because of the laser. So because we are incidenting a laser, the population is going from the ground state to excited state and coming back. But in the real world, this doesn't happen. This doesn't go on forever. As we increase time, there is damping, and I will talk about that next. So just to clarify, so there are different cases that we were talking about. So first case is when you're considering the variation in capital omega. Second case is when you're considering the variation in frequency. Third case is when you're considering the width of the frequency that you're applying. Then fourth and fifth cases are little advanced. Those are which those are what actually the question is about. So with and without the decay in the system. So we have right now not talked about the spontaneous emission at all. So everything that we have derived till now only applies for a system that doesn't interact with the environment. So basically, we have not incorporated the interaction of vacuum at all. If we do that, then the decay terms come into picture, and then the system has a decay in it, and we have to consider the interaction with the environment as well. Because our system basically is light and atom, and if the oscillations are happening just because of these, then those are stimulated processes, and there is no decay in those processes. But then if our system is interacting with the environment, and we have to consider that interaction as well, which is what happens in the real world, because in the real world there is no process that is ideal. There is always interaction. You cannot isolate your system from the environment. So there is always interaction with the environment, and that's why there is a decay in the system always. So spontaneous emission is always there, but it's just that in this formalism, till now we have not introduced that. That's why whatever Rabi oscillations and everything that I'm talking about till now has been only in the case of where decay is zero. So I have not considered spontaneous emission at all. The last thing that we can differentiate in terms of the light atom interaction is whether we have a single level atom, which is like just a two-level system, or we have a multi-level atom, which means that there are more than one excited states uh, other than the ground state, other than the one that we have specified. So these two are the advanced regimes, which you will need like left Gordon coefficient formalism. You will need multi-level atom understanding. So we won't go there, but we will talk about this thing with the decay and without the decay. So if we want to talk about that, then I have a I have one special case for you. So there are two cases that we can talk about. One case is where we consider that there is a decay in the system. What do I mean by decay is you are considering spontaneous emission. So without the decay means without spontaneous emission. What this means is if I have excited the population to the excited state, it will stay there if I don't excite it back, if I don't de-excite it back. So if I basically give a pi pulse, then what will happen in this graph is if I choose a laser such that omega t is equal to pi. This condition is true. If this condition is true, basically I will what if I start with the atom in the ground state, what will happen is I will slowly take the atom in the excited state, and it will stay there because if there is no interaction with the environment, it has to stay there if I have cut down the laser source. So if I only give the laser source for a time where omega t is equal to pi, the capital omega t is equal to pi, then all the population I can transfer to the excited state. In that case, the population will stay there, which is not what happens in the real world, but just to consider an ideal scenario, this is how we can understand the system where we don't consider decay at all. So if there is no spontaneous emission in the system, then when you excite from the ground state to the excited state, the atom will stay there because it's not interacting with the vacuum, it is not interacting with the environment. So these are the two cases in Rabi oscillations. Rabi oscillations without the decay and Rabi oscillations with the decay. So Rabi oscillations without the decay, what you will see is you have excited all the population in the first state. Then if you keep incidenting the laser, then after this is time in x-axis, this is time. So time going to infinity, and this is the population. So the population will oscillate from the ground state to excited state, and then these oscillations will go on forever because there is no de-excitation in the system because of the interaction with the environment. So if you are not considering the decay at all, so basically you're considering that not the Klebsch-Gordon, you're considering that the Einstein's A coefficient is zero, then in that case, this Rabi oscillation case is true, because you will get oscillations till infinite time. So your system will keep oscillating from the ground state to excited state like this, and the electron will go from the ground state to excited state till you have incidented the laser. So till the point that if you are continuously incidenting the laser, if your laser is on for a long time, the oscillations will keep happening for a long time, and there is no time period after which they settle down. So the oscillations keep on going if there is no interaction with the environment. But like I said, so now we'll consider the real world example. So this is more of what happens in the real world, that if you have now Rabi oscillations with a finite decay, so there is spontaneous emission that is happening as well, in addition to the stimulated emission that you are carrying out, stimulated absorption and emission you are carrying out. So because of the laser that you have incidented on the atom, there are two processes that are happening: stimulated absorption and stimulated emission that you can see in this graph. In addition to those, now there will be another process, which is the third process, which is the spontaneous emission. So if you now have a third process that is contributing to the decay of the population in the second state, then you basically now have two avenues by which you can come down in population. So the population in the excited state now can decay or can come down now by two ways, either by stimulated emission or by spontaneous emission. And that's what happens, that if you keep your laser on, then after a certain amount of time, it will decay down, and then that decay rate is what is decided by the spontaneous emission rate. So this is how the Rabi oscillations figure will look like if you have the atoms in the real world, and if you excite the two-level systems in that. If you're on resonance, so if you are on resonance, and if your omega t is same as pi, um, and if you keep increasing your omega t, so if you start with omega t equal to 0, and then as time goes to infinity, what you will see is you'll see a saturation effect where this settles down at half the value. So what you get basically is, in the real world, you'll get oscillations and then you'll get decay of those oscillations. So this is what you get in the real world, where you get an exponential decay of your probability, and that decay rate is actually determined by the spontaneous emission. So now with the real atoms, what will happen? So with the ideal atoms, what used to happen was, if you have a two-level system and if you're incidented a laser on it, then the oscillations will keep happening from the zero to the excited state. The electron will keep going up and down, uh, depending on whether you are away from the resonance or you're on resonance. So if you're on resonance, then these oscillations will definitely keep happening. Unless now, if you consider a real world atom, in real world atom now, if you have a two-level system and if you are incidenting a laser, the oscillations will start, but then the amplitude of those oscillations will decay down, and the amplitude of those oscillations will actually the probability of taking the system to the excited state. So the probability of taking the system in the excited state using the laser actually decays down, and then that decay rate is given by the spontaneous emission of your system. So what happens basically is, because of spontaneous emission, now you have a limit. Now you can't excite the entire population from the ground state to the excited state, because there is another possibility by which the electron can come down. So that's why the graph that you get is, initially you can start by driving the system entirely in the excited state, and then the probability of exciting to the excited state starts going down and then decays, and then these oscillations are actually same in frequency. So they are still periodic, but the amplitude goes on decreasing, and the amplitude settles down after a while, after the time period of the decay rate. What happens is, you basically at the end of this process, if you keep the laser on for long amount of time, at the end what you will get is half the population is in the ground state and half the population is in the excited state. So in case of ideal atoms, what you get is, depending on the frequency of the oscillations, depending on how long you're keeping the oscillations going on, in the ideal system you can get from 0 to 1 entire probability. So at infinity as well, depending on where you are on the time interval, you will get the populations in both ground and excited state. But in real atoms, if you see at time t equal to infinity, what you will get is half the population will be in the ground state and half the population will be in the excited state. So the equal mixture of ground and excited state population. That is what you get with real atoms. So this is the result when you have an atom and you have incidented light on it, and there is spontaneous emission. So basically, your system is interacting with the environment. Then what you will get is the decay of this Rabi oscillation. So yeah, this is very interesting, because this is what tells us that the real world behaves very differently compared to the ideal world that we have been talking about. So in real systems, finally you will get equal population, and in ideal systems, what you will get is continuous oscillations between the ground and the excited state. So I hope this clarifies the doubt that was there in the chat. So yeah, so now the second point that I wanted to talk about today was about the block sphere representation. So I hope there is no doubt with Rabi oscillations concept. If there is anything that you guys want to ask, then you can ask on the chat. Um, I'll stop and explain again. But I think it should be clear that these are the Rabi oscillations with and without the decay rate. So, and this concept of Rabi oscillation is very useful actually to represent anything that is two-level system. And that is any two-level system is actually characterized by their Rabi oscillations. There is another system that is very useful for characterizing two-level system, that is excited. That representation is block sphere representation. That gives you the best visualization for a two-level system. So if you search for block sphere, there are a lot of YouTube videos as well, which give you nice intuitive explanation of what is block sphere and how you can use that block sphere in a two-level system formalism. So this block sphere representation, which I am going to tell you about, these this helps you visualize the system, and this helps you visualize the time evolution of the system. So if you have a qubit which has again 2 bits, so that's a two-level system. If you have a spin half particle, that is again a two-level system. Both these you can talk about or represent in terms of block sphere representation. So what is a block sphere? Block sphere is basically one sphere where the North Pole and the South Pole gives you the ground state and the excited state. So if you have, you can determine any, you can assign any one state to any one of the poles. It doesn't matter. But one of those poles is the ground state basically, and one of those poles is an excited state. So let's say this is the ground state and this is the excited state. So if you draw a sphere and if you assign the two poles as the ground and excited state, then you can visualize your system's evolution. Whether your system is in the ground state right now, then it will be a vector pointing towards the ground state. And if your system is in the excited state, it will be a vector pointing towards the excited state. So what are the rules that you need to know while drawing these diagrams, drawing block sphere diagrams to represent your two-level system? Why do we need these diagrams, or what these diagrams convey is what is the state of your current system? So how much of the population is in the ground state? How much of the population is in the excited state? Is it in the superposition? So if some population is in the ground and excited state, then there is a superposition. Whether it's a pure state, whether it's the mixed state, we have talked about pure and mixed states in earlier when we did density matrix formalism. So pure states are something that have that can be defined as a single vector, single wave function psi. And mixed states are something that you get when you have multiple particles. When you are talking about a statistical ensemble, that's when you get the mixed state. So pure state is something that is for a single particle and just a specific wave function. So no superposition. But in mixed state, we do get superposition. So if we want to then visualize and still represent both of these pure and mixed states in the same diagram or in the same, just using a block sphere, then this formalism is pretty useful. So what are the rules? That, like I said, the ground and excited state form the two poles of the sphere. The pure states lie on the circle, like on the radius of the circle. So basically, the radius of the circle. Okay, so let's start from like visualizing, like mathematically. Let's talk about two-level system. So any wave function psi, let's say, which is a pure state, that can be represented as the superposition of two states, which is for us ground state and excited state. So this is how we write the superposition in terms of the coefficients alpha and beta. If this is the case, then if we are considering a normalized system, a normalized atom or something, a normalized two-level system, then you know that the probabilities have to add. The coefficient square gives you probabilities, so probabilities have to add up to 1. So that's why if we write the system as a two-level system, which is a superposition of the two bits, then we can already write this expression that alpha square plus beta square gives you 1. So now, because the amplitudes, so these are the amplitudes of the superposition, right? So if you have your two-level system, then the coefficient for first level is alpha and the coefficient for second level is beta. But now the problem arises because these amplitudes can also be complex numbers. So in addition to real part, it can also have an imaginary part. And then, so that's why each number alpha has actually two components, which is real part of alpha and imaginary part of alpha. Similarly, beta has real part of beta and imaginary part of beta. So basically, you have four numbers that you need to know in order to express or in order to talk about a system which is a superposition state. So if you have a two-level system and you have two coefficients for it, then each coefficient has real and imaginary parts. So you basically need four numbers to specify your system. So you need four dimensions to specify everything about the system. So, but four dimensions, again, it's difficult to visualize. It gets very messy to draw or imagine anything. That's why what we want to do is we want to reduce from 4 dimensions to 2 dimensions. So we have to eliminate the 2 dimensions. We do that always in physics because like you have done several number of times, I think, in center of mass frame, we go from two body to one body formalism, we go from three body to two body formalism, because reducing the dimensions basically makes our problem simpler and it makes it mathematically solvable as well. That's why we put some constraints on this to reduce the four-dimensional space to two-dimensional space. What are the constraints? This is one constraint, that alpha square plus beta square is equal to 1. So even if you know one coefficient, you can get the another coefficient in terms of the square. So you already know the real part. So you don't have to consider that. So this is the first constraint. And the second constraint is something that comes in the phases. So I'll talk about that. But alpha and beta can also be talked about in terms of Rabi frequencies and detunings. So we have talked now a lot about Rabi frequency and detuning. So this is Rabi frequency and this is the detuning. So detuning means again the difference between the atomic resonance and the difference between atomic resonance and the laser's frequency. So if you're talking about these two things, then we can represent the two coefficients in terms of Rabi frequency and detuning, which are the experimental parameters that we have been talking about a lot. So then what we want to do is we want to use these two things, capital omega and delta, as our basis set. And then using this set, we want to represent everything regarding our two-level system formalism. So, and this formalism is useful even to get density matrices. When we move to density matrices, this block sphere formalism is still useful. So if you notice that alpha and beta have, so I'm just reading this out. If you notice that alpha and beta have both two parts each, real and imaginary, like we talked about. So the amplitudes don't need, the amplitudes actually can be represented by just two dimensions. So we are representing the same psi now in terms of theta and phi. So this is the expression that we need to convert to if we want to go from this expression, which has four things, because alpha and beta are both real and complex. So that's why there are four dimensions. But we want to represent everything in terms of capital theta and phi, because the relative phase also plays an important role. So if you now consider the phase, the phase is always relative with respect to something. So we are always interested in the phase between the two levels. We are not at all interested in the phase of individual level, which is the absolute phase. So if you are considering the ground state, if you are considering the excited state, what is the phase difference between these two levels? That is the important. That is the important concept, or that is the important physical thing that is there in the two-level system, that the phase difference between the two levels. There is no importance for a phase of one level because it can be arbitrary. Similarly, excited state specific phase doesn't matter at all. What matters is what is the phase difference between the two levels. So that way as well, we have reduced another dimension. So that's why in one, so the two dimensions that we have considered here, that we have reduced down to, is one constraint was that the probability has to be 1. So that's why the alpha square plus beta square has to be equal to 1. So that gives you one constraint, and another constraint is that uh, in, you are only interested in the relative phases. That's why you need phi 1 minus phi 2. So there is a simple derivation how you can go from equation number. So this is the equation number 1, and this is equation number 2. So there is a simple derivation how you can go from 1 to 2, and that you can do on your own, or I will also send the link uh, to a video that explains this in like very few limited number of steps. So what you're doing essentially is going from the Cartesian coordinates to the angular coordinates, where you are now representing in terms of r, theta, and phi, which you do a lot in atomic physics because that's the basis in which we write down hydrogen atom and we do all the calculations with atoms in that basis, which is a spherical basis. So spherical basis has r, theta, and phi. Amongst that, the r is a constant here because the radius of the sphere, like I said, I have talked about in terms of alpha square and beta square. So that's the radius of the sphere. So the sphere that we have talked about to represent the two-level system, the radius is given by so the radius has a constraint that it cannot be more than one, because the probability of the system cannot be more than one. It has to add up to one. So that's why that's one constraint, and another constraint is in the phases. So that's why we don't care about what's the phi 1 and phi 2 for these two levels. What we are interested in is what is the phase difference between these two levels. That's why when we go from Cartesian coordinates to spherical basis, in spherical basis, because r is equal to 1, that's why we have just theta and phi. And that's why we have just two dimensions now in which we can express the entire two-level system state. So this basically gives you, that's why the representation is now 2D in terms of theta and phi. So this representation basically gives us incredible power now to go and write everything in terms of just Rabi frequency and detuning of our laser and atom interaction. So if we have the sphere where we can consider whether the system is in the ground state or excited state or in the superposition, or how to represent that, everything just boils down to knowing what is your Rabi frequency of your system and what is the detuning of your system, how much away you are from resonance. If you know these two things, you can represent everything in terms of these two things, and you can represent it in a sphere. And that sphere is what we call as the block sphere. So you will maybe hear this a lot whenever we are talking about atomic physics and the representation. Even in qubits, even in quantum computing, people use block sphere a lot, because in quantum computing as well, you are using this concept of two-level systems, and what is the current state of your two-level system can be represented really well and expressed really well in terms of block sphere formalism. And this is how the block sphere formalism comes into the picture. So uh, omega is Rabi frequency again, and delta is detuning. And we have just pure math wise, we initially had four dimensions because alpha and beta had complex parts, so both real and imaginary parts. So that's why we have reduced from four dimensions to two dimensions, because of the two constraints that I am talking about always, is that we only care about the relative phase that is real. That's why one dimension gets reduced, and the total probability is equal to one. So that's why another dimension gets reduced. That's why we can talk about the two-level systems in just simple two-dimensional space, even though there are four quantities that are unknown to us, which are complex coefficients, so real and imaginary parts of both coefficients. So the four unknown things that are unknown to us are actually these things, and because each of these, so alpha has two terms, beta has two terms. So actually four coefficients were unknown, but still we can represent it in two dimensions by using a block sphere. That's why block sphere is like a really important uh, way of representing the two-level system. And the two-level system can be anything, like a qubit or like a spin half particle or atomic system, like we are talking about here. So that's why block sphere formalism and Rabi oscillations. These are the two concepts which are really important when we are dealing with light atom interactions. And these come about actually after solving the equations that we have derived. And we started, if you remember, we started with just dipole interactions between light and atom. And then we wrote the Hamiltonian. We solved the Hamiltonian using Schrodinger's time-dependent equation. And then the Schrodinger's time-dependent equation later simplified in terms of two coupled differential equations. And those two coupled differential equations, if you solve for a specific case where you have taken a monochromatic light, which is a light of specific frequency, then you get Rabi oscillations. And if you have Rabi oscillations, then there are two types of Rabi oscillations that are possible. Either Rabi oscillations can be with a decay or without a decay, depending on whether the system is ideal, whether the system is interacting with the environment or not. That is Rabi oscillations. And this concept of block sphere is how you can represent a two-level system, whether it is excited, whether it is de-excited, or whether it is in the superposition or not. So if you now want to if you now want to write the process of Rabi oscillations just in terms of block sphere, then what you can write is, so you have this block sphere, and then you have the poles, which is the ground state and the excited state, and then you have the origin here. So basically, if your atom starts here in the ground state and the final journey of the atom is in the excited state, so let's say you have another sphere. So if this is the excited state, then what you can imagine what's happening is the radius vector here is doing a precession action. So this vector is doing a precession either clockwise or anti-clockwise. It is precessing, and this precession in a block sphere is basically what you can represent when you are on resonance. So if you are on resonance, and if your omega t is going from 0 to 2 pi, let's say, then in block sphere representation, if we want to represent what do you mean by Rabi oscillations, then Rabi oscillations basically means in this formalism, in this representation, it is just that this radius vector is now precessing along a specific, like precessing along the entire sphere in a periodic fashion. And that's why now you can see the elegance of this formalism, that the block sphere can represent like a system's current state. And you can see that the time period of these oscillations will be, if you do it for just omega t equal to pi, then what you will land up with is, if this was the initial state, and this will be the final state. So initially you started with all the population in the ground state, and final state is where you got all the population in the excited state. And this will keep happening until a point where if your system is ideal, then this precession will keep happening. So this is basically another way of just representing the same system or the same process that is happening, which is Rabi oscillations, in a different notation or in a different formalism. So, and this will prove very useful whenever you are considering a mixed state or pure state, and whenever we are considering density matrices. This representation of block sphere will prove very useful. That's why I'm emphasizing this block sphere a lot. So anyway, these are like the two concepts that I wanted to mainly cover today, which is block sphere and the Rabi oscillations. I think in the next lecture, what we will cover is optical block equations. This is like the final thing in this derivation. Optical block equations, and then once we have done optical block equations, which will involve density matrix formalism, then with optical block equations, we can basically understand everything about the light atom interaction. And then what remains is just like some fun experiments that you can do with simple scenarios that you do in the lab. And you can create some scenarios like if you apply a magnetic field, if you apply electric field, depending on that, if the levels shift or not. So we can consider different scenarios, and we can consider what will happen with those scenarios as well. And we'll also see the saturation concept in the two-level system, that if you have a very large intensity laser, then the transition can be saturated. And then what happens after the saturation, what happens before the saturation. So, but remember, I think today's main takeaway is that there are two important things that we always talk about when we are talking about two-level systems interaction with atom. Is one is the Rabi frequency, and second is how far detuned you are from the resonance frequency. So the detuning and the Rabi frequency are the two most important parameters. And in terms of those parameters, we can represent everything that happens in two-level systems. And I think this is what I wanted to talk about today in light atom interactions. So yeah, I guess if you guys have any doubts, you can ask uh, anything that you guys feel you are confused in, or you want me to repeat about today's lecture or any of the previous lectures at all. Otherwise, we will meet in the next lecture, and we will talk about optical block equations. I think it's a good idea to read Foot's seventh chapter, because now I think we have covered a specific, like we have covered enough portion of that chapter for you to even understand by yourself uh, the same formalism that we have gone through. but I think maybe you don't have that much amount of time on your hand, then it's fine. It's fine if you don't read the whole chapter as well. But yeah, I will definitely talk with Nitin sir, I think, about this. Um, if the lectures are like maybe a big load on you in terms of academics, then please let me know. Yeah, whatever you guys feel, you can maybe message on the group as well. You can even email me and let me know your feedback. And yeah, I guess we'll meet in the next lecture. Uh, this this is what I wanted to cover for today's lecture. So I'll see you next time. Have a nice day.